the recording. So welcome everyone to this One World Mathematical Physics seminar of IAMP. For those of you who might be joining us for the first time, IAMP is the International Association of Mathematical Physics, and this is our regular seminar series. So if you want to find out more about the association and then about our seminar, please see the link in the chat. And you can also join our mailing list to get announcements for our seminars on the regular basis. Okay, but now let me introduce our speaker of today. So it's a great pleasure for me to welcome Christoph Kopper, who's going to talk about asymptotically free scalar fields. And just to remind everyone, this seminar is being recorded and the recording is going to be available on our YouTube channel. So Christoph, please take it from here.
Oh, thank you very much, Kasia. And thank you very much in general for the organizers for inviting me. So Kasia, Marcello, Hal and Jan. So I would like to talk a bit about recent work which I have done on scalar fields in the framework, analysis in the framework of the flow equations of the renormalization group. In fact, well, I will come to all this again. When I started this work, the motivation was not so much to find asymptotically free scalar fields, but rather to work with the flow equations in a non-perturbative context. And when analyzing the flow equations from this point of view, I more or less fell then onto this possibility that there might be asymptotically free solutions for scalar fields. And so to some degree, this was a bit of an unexpected outcome of a number of years of work on this non-perturbative aspects of the flow equations. So I give you an outline then of my talk here on this next transparency. So I will start with a few introductory words. Then I will remind the general context of the flow equations. Then I come to the mean field or local potential approximation, to which I will limit what I'm going to say today. I will come to solutions, a certain class of solution of these mean field flow equations. Then, as you probably know, asymptotically free scalar fields are in some sense unexpected, and there are certain results in the literature which go into the opposite direction. And so I will talk about in particular about, I think, the rigorous results which are the most clearly stated and which go into the opposite directions are those of a CMP paper by Giovanni Felder from 1987. And so I will comment a bit on that. Then I will come back to the trivial solution, which is normally the one which is expected for scalar fields in 4 dimensions. And in the end, I will maybe comment a bit in a somewhat more qualitative way on perspectives of how one might go beyond the mean field approximation for this subject. So first, some introductory remarks. Probably you have heard, because it has also become a gain of scientific actuality, about the triviality theorem for scalar fields, which goes back then to work of Fröhlich and Eisenman 40 years ago, and which was taken up again by Eisenman and Kopper in recent years, and which can be stated in very short form in terms of the sentence: scalar 4-to-4 field theory is trivial. So if you have a scalar field in 4 dimensions with a 5-to-the-4th interaction, which is a renormalized interaction you could have for the symmetric for the symmetric scalar field theory, then the theory is trivial, which means that the truncated or connected 4-point function for this theory vanishes in the continuum limit. And then there are further results which say that if the truncated 4-point function vanishes, and also the higher endpoint functions truncated endpoint functions vanish at the same time. As usual, if you have such a theorem, the theorem is based on certain assumptions, and the assumptions which are made here are that these studies by Fröhlich, Eisenman, Duminil, Kopper normally start from a lattice regularized version of this theory, and then they study the continuum limit of this lattice regularized version. They study the symmetric phi to the fourth theory without symmetry breaking, that is to say with a positive mass term. And the result, which is based on correlation inequalities, applies in the first moment to one or two component phi to the fourth theory. So if there's an internal symmetry, there might be two components of an O2 symmetry for the field, but or otherwise only one component. On the other hand, the theorem is strong in the sense that it does not put any restriction on the size of the Baire coupling, which appears in the lattice regularized version of the theory we start from. On 40 years ago, the theorem was based on the assumption that this model has infinite wave function renormalization, which is normally supposed to be true just from perturbative knowledge of these theories, and the recent progress by Eisenman and Duminil-Kopper frees the theorem from the assumption on the wave function renormalization, so there is no assumption anymore necessary on the wave function renormalization. On the other hand, so this makes the analysis much more complicated. So this Eisenman and Duminil-Kopper analysis is also in a certain sense a multi-scale analysis in the sense of the renormalization group. This theorem applies to phi to the phi for fourth theory, as one says. So the Baire action then is supposed to be a lattice, in this case, lattice regularized version of a theory with Baire action of the kind which I have written here in the last line of the transparency. So there are the quadratic terms, which to some degree maybe are present already in the Baire propagator. And then there is a phi to the 4 interaction, which is a positive coupling constant lambda. It has to be positive in order to have an action which is bounded from below. So this is our statements in the context of mathematical physics. One can then look a bit into what it means in more general context, maybe leaving the strict context of mathematical physics. And then the first thing is that this triviality theorem was also corroborated by numerical studies already in the 80s, by in particular very thorough work by Lüscher and Weiss. Lüscher also has written a paper which made similar statements as Eisenman and Fröhlich made in the 80s on quantum electrodynamics. So in principle, there's also, even it is not strictly a mathematical physics statement, there is also a credible and very proper statement that this triviality hypothesis should in principle also extend to quantum electrodynamics. That's an interesting paper from 1990, which maybe could be cited a bit more often in this context. And from the theoretical physics point of view, there's also a general belief that this triviality statement, that the physical argument which is at the heart of this triviality statement is the fact that the theory is not, from the point of view of perturbative quantum field theory, is not asymptotically free in the ultraviolet. Theories which are not asymptotically free in the ultraviolet, but rather in the infrared, typically suffer also in perturbation theory from certain inconsistencies, which are sometimes baptized presence of the so-called Landau pole, which is a pole which appears in perturbative expansions at high energies if you do not have asymptotic freedom in the ultraviolet. And so the general belief is that these triviality statements in some sense should extend to all theories which are not really asymptotically free in the ultraviolet. And this is then, in a certain sense, a disaster for the mathematical status as a standard model of particle physics, because in the standard model of particle physics, you only have really one sector which is separated from the rest and which is asymptotically free in the ultraviolet, and this is quantum chromodynamics. But if you look at quantum chromodynamics as an isolated theory, then you find this infrared problem, which is really far beyond scope. The methods of rigorous quantum field theory is kind of millennium problem. I think millennium problem in a relatively strict sense. And so one expects then that the standard model of particle physics is completely out of hand from the point of view of mathematical physics. Now, I would, in the subsequent analysis, which, as I said, is motivated by the flow equations of the renormalization group, do something which, from the point of view of the renormalization group, is completely natural. Namely, I would like to scrutinize a bit the assumptions of this triviality theorem concerning the form of the bare action of this theory. Now, there are remarks here, but I think they do not consider. So if you have questions, maybe ask them directly, then I can maybe answer also directly. So I would like to do something which is relatively natural from the point of view of the renormalization group, where you see even if you start from a bare interaction which has this phi to the 4 type of structure, and you integrate it only for one renormalization group step, it will immediately develop terms of all orders in phi, or if you consider the even theory in phi squared. And so it is quite natural from the point of view of quantum of the renormalization group to embed the problem of the scalar field in 4 dimensions into a context of non-polynomial bare interactions, and to look a bit what happens there. On the other hand, you know that these problems in quantum field theory are very complicated, and so my work, as far as my results are concerned, is based on the mean field approximation, to which I will come soon. So first I will now go to introduce the general context of the renormalization group equations, and then in the chapter afterwards I will come to the mean field approximation. So the flow equations of the renormalization group in the general context are obtained in the following way. You first define your theory, or as Raymond Stora said, it's just not really a definition, but rather the formulation of an opinion. But in any case, you have to do something you start from, and what we start from is then a theory which makes appear in just one scalar field, which we call phi. And if this theory is even under the symmetry phi goes to minus phi, we can restrict ourselves to even polynomial, to even monomials in phi. And so our bare action would be something of the kind I have written here, where here there is this wave function term, which later on will in any case not play any role, because we go to the mean field approximation, which neglects fluctuations of the field. And then there might be powers of phi squared of any exponent, and this would then be the bare action we start from. There are of course certain conditions on the bare action. As I said already, it should be bounded from below, but let's just say this is the actions which fix the general context. And then to start the renormalization group flow, you say, I'm studying this theory with a flowing propagator. And this flowing propagator is a propagator which first only has basically, in a certain approximation, only support in a certain interval of energy or momenta, or if you go to Fourier space and distances. So here I define a flowing propagator which makes appear 2 positive parameters, alpha 0 and alpha. Alpha 0 is the smaller one of those, and alpha the bigger one. And they vary between 0 and infinity. And if you take really alpha 0 and alpha infinity, you just, from the integral, just gives you 1 over p squared plus m squared, which is the propagator of a Euclidean massive theory. And then now if you, the renormalization group in this context consists in saying we start first from a propagator which is 0, so alpha equals alpha 0, the integral is 0. We leave the alpha 0 to have an ultraviolet cutoff, which makes us get rid of certain technical problems, and then we let evolve the parameter alpha from alpha 0 in direction of bigger and bigger values, and this means that we integrate out more and more momenta and come closer and closer to the real physical theory. And if we do this in the context of a continuous flow, we will the derivative of this propagator with respect to the flow parameter alpha will play a certain role. And you see, if you derive this integral, we get here just this exponential, which says that basically this derivative is very much suppressed if the momenta which you have are much bigger than 1 over alpha. If p squared is much bigger than 1 over alpha, nothing more happens basically if p squared is much more bigger than 1 over alpha. So alpha serves also as an infrared cutoff. In principle, one would say here first, in the first moment, if the theory is massive, we do not really need an infrared cutoff, but we want to follow the evolution of the theory from the ultraviolet to the infrared direction. And in this case, this flow parameter rather serves to analyze the theory, even if there's no really hard infrared problem to solve. So these are the first or the basic ingredients for this renormalization group flow. And then we come to a definition of the so-called Wilson effective action. Namely, if you look now at our bare action, which was this action which contained the sum over all these monomials in phi, and you integrate it with a Gaussian measure, which is characterized by this covariance C alpha 0 alpha, which I introduced before. Then you come and the random variable here is capital phi. Then you obtain an effective action at the scale alpha, which is depends on the random variable small phi. And from the point of view of quantum field theory and of the perturbative contents of quantum field theory, this bare action here, this Wilson effective action here with upper indices alpha 0 alpha is then the generating function of free propagator amputated connected endpoint functions with free propagators here alpha 0 alpha and bare action L0. So something which is well defined in terms of Feynman diagrams. There are no divergences in these Feynman diagrams because alpha 0 is an ultraviolet regulator. And then this is a way in which you can view things in the framework of perturbation theory. Then the question is, of course, under which conditions this would also make sense beyond perturbation theory. Okay, and then once we have this definition of this Wilson effective action, so the real aim would be then to construct the action L0 infinity, which would be the fully integrated out theory, the physical theory with the generating function of the full Schwinger functions. This effective action now obeys a differential equation, a functional differential equation, which is obtained by performing Gaussian integration by parts in this expression here. So you can look at this expression here. You can take a derivative with respect to this flow parameter alpha. Then this derivative acts on the right-hand side on this Gaussian measure here. And then there are certain relatively easy to memorize formulae on the derivative of Gaussian measures depending smoothly on a parameter. And if you use this integration by parts formulae, you arrive at the flow equations of the renormalization group for this Wilson effective action, which takes this form here. So there is this derivative with respect to the flow parameter of this Wilson effective action is given by a linear term and a quadratic term in this action L. This comes directly from this Gaussian integration by parts. The linear term contains two functional derivatives with respect to the field phi, of which L is a functional, and there appears that this derived propagator which we introduced before between them, just this exponential e to the minus alpha p squared plus m squared. And there's a quadratic term where you have two contributions which are also linked with, through this derived propagator. The notation which I employ here is this shorthand notation for scalar products in Euclidean space. So this expression here, for example, means in position space that you take the functional derivative with respect to phi, the kernel of the propagate of c dot, going from y to x, and the functional derivative at x, all of it integrated over x and y. So this is this functional flow equation, which then leads directly to the Polchinski type flow equation, which is obtained once you once you assume that you can expand this Wilson effective action in moments. So here I again have this Wilson effective action. And if it has an expansion in moments, which I have written here directly in momentum space, also using translation variance, then we can derive from this equation here, from this functional flow equation, also a flow equation for the moments. You see translation invariance appears in the form of this four-dimensional delta function of the sum of the momenta. Then you have Fourier transformed fields, and then you have these moments. N indicates here that you have to take the nth moment of this expansion in moments of the functional, and in Fourier space it becomes also a function of the momenta. It's a completely symmetric function because these are moments all with respect to the same field phi, so it's completely, so Bose symmetry is also implemented here through the fact that this function L hat is completely symmetric with respect to the p's. Translation invariance is taken into account by the fact you have here the four-dimensional delta function. And then if you rewrite now this function, you expand with respect to moments here, 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 and here. And then you take the contents of this equation for the nth moment. You get the following equation, which I have written here. So are certain combinatoric factors, which are easy to visualize. And apart from this, the first term says that you have to, the first term in this flow equation said we had this term with two functional derivatives, which then relates the nth moment to the n plus second moment here. And these two functional derivatives were joined together by a derived propagator c dot of alpha, and all this was integrated over, and taking into account the translation invariance gives us this expression here, where we have to integrate over this momentum p, which I did not explicitly indicate because formulae often rapidly become too long. And then there was a second quadratic term, and the second quadratic term, there appears then a product of two of these moments, with the condition that the sum of n1 plus n2 gives n plus 2 again, because there were two functional derivatives involved on the right-hand side of the previous flow equation, and the whole thing was again joined together by a c dot of alpha. So these are then now the flow equations of the renormalization group, boiled down to moments of the Wilson effective potential. Here there's a simple symmetrization because we always have to produce symmetric functions. Here you see these functions, these two functions are symmetric, but when you multiply them, they are not symmetric under exchanges of these momenta. So the whole thing has to be symmetrized here with respect to P1 up to Pn. Okay, and then I would say for my personal work, but also for the work of many other people, these equations played an important role in analyzing the problem of perturbative renormalizability. So there was an important observation also from the 80s by Joe Polchinski, who observed that these equations, when also expanded in the number of loops, which I did not do here. Here I did only expand in moments, but not in loops. If you also expand in the number of loops, which produces the perturbative expansion, then provide an airtight inductive scheme to prove perturbative renormalizability. And having at a disposal differential equation plus an inductive scheme, then was really a very strong additional ingredient in studying this problem of perturbative renormalizability. And we got, and others got, interesting rigorous results on perturbative renormalizability from these flow equations, which could not be arrived at by other methods. So it really turned out to be a very fruitful and scheme really adapted to mathematically rigorous analysis of perturbative correlation functions in renormalizable field theories. So as I said before, are there any questions to this? This is still, let's say, to some degree introductory. So now I want to come to non-perturbative analysis in this simplified context of the mean field or local potential approximation, which in the first moment consists in neglecting fluctuations of these moments. So as the name says, so we replace these functions of the momenta L hat of P1 to Pn by their values at zero momentum. The values at zero momentum are just the mean values taken over the coordinates per unit volume. Typically in a massive theory or in a theory with infrared cutoff, there's a tree decay between the different coordinates of these correlation functions. So if you look at this integral here, typically it will have a divergence proportional to the total volume. And so if you divide by the total volume, you get something which converges. And you can see also for perturbative analysis or whatever that these things here on the left-hand side of the equations exist in perturbation theory. And now we can analyze these objects here, these mean field objects, again with the flow equation. And what does the flow equations give for this object? Well, I'm writing this immediately, but I'm writing it in a slightly rescaled form. So I'm not directly analyzing these objects, but objects which I call Fn of a function of a parameter mu. And these objects Fn are related to An just by multiplication by n. N is the argument of the moment. Then there's a constant involved here, which comes just from the Gaussian integral over this e to the minus alpha p squared, which if you scale it out, it simplifies the equation. And then there's a constant here, which is a power of the flow parameter. And in fact, for those who know a bit about perturbative quantum field theory, this is the so-called engineering dimension of these objects here. These objects here have in units of mass, they have a certain dimension, and it is good, useful for the analysis of these mean field flow equations to scale out this dependence on the mass scale. And so if I take here, if I multiply by this power of the flow parameter, lambda has dimension 1 over mass squared, I get something which is dimensionless, which does not have any mass dimension anymore, and the flow equations become simpler in terms of this quantity. And then I write also these quantities in terms of the logarithmic scale. So we said alpha 0 is the ultraviolet cutoff, alpha is the flow parameter, which is bigger than alpha 0. So this logarithmic scale varies between 0 for alpha equal to alpha 0 and goes up to maximal value. Could be infinity if alpha goes to infinity. Here there's a value of the constant, which is not so important. And then I would also perform another relatively innocent simplification, namely, I will rather restrict now alpha to the interval, not alpha 0 to infinity, but alpha 0 to 1. And then this 1 would basically be the infrared cutoff, which is normally furnished by the mass. And then just to simplify the appearance of the equation subsequently, I will consider then alpha in the interval 0 up to some big value logarithm 1 over alpha 0. And on the other hand, if I put the infrared cutoff on the parameter alpha, I will instead put the mass equal to 0. This is, as I said, this is rather to simplify things from the point of view of appearance and digestibility, but it's not really a fundamental importance. So if I do this, then we have written the flow equations for these objects L hat. And if I do now this rescaling, and I write everything in terms of mu, I can write now the flow equations for these objects Fn, which are dimensionless, as I said, and a constant which has been taken out. And then this flow equation takes a relatively simple form. Namely, if I solve it in terms of n+2 of mu, it takes this form here. So I've written it a bit differently from what I did before. You see here I had the flow equation on the left-hand side. We had the derivative of ln, and the ln+2 appeared here. Now, if I neglect fluctuations and I take out the dependence on the p's, then I can perform this integral here explicitly. This gives the constants little c, which have been scaled out. And then I get a constant times the ln+2. And in the rewritten mean field flow equations, now the thing I've written things such that now this ln+2, which has become fn+2 in the mean field approximation, appears isolated on the left-hand side. And then you see that this fn+2 appears now as a function of functions fn, which have a lesser n than n+2. So the maximum value of the n's, which appears here on the right-hand side, is n here and here. And here I'm summing of n1 plus n2 equals n+2, but the ni already have to be at least equal to 2. So here n1 and n2 are also limited to values up to n. Here's a misprint, by the way. This should be n2, n index 1 and index 2. These are n1 plus n2 equals n+2. So I've written this flow equation here, and mean field flow equation in this form here. And again, just to remember what we are doing, we said these Fn flow parameter 0 are the bare amplitudes. So this is really the objects which appear in the bare action. And if we have fully integrated out the thing with our technical simplification of saying we integrate from 0 to mu max, then the Fn of mu max are to be viewed as the physical mean field amplitudes, those which really describe in the mean field approximation, the physical model, the scalar field theory, which I'm interested in. And now if I'm writing the flow equation, this flow equation written in this way is a bit contrary to the spirit in which you normally treat dynamical systems, because these flow equations written for the moment are an infinite dimensional dynamical system, because we have all values of n are admitted, and normally you solve then these or make statements about the solution of these equations by integrating them here. Then it turns out when you want to do this, you will find that typically this is an unstable process. So you cannot really solve the system exactly. And if you solve it first by certain approximations, and then you try to iterate by successive integrations, then the system turns out to be unstable. And so the reason for writing the flow equations in this way is then that we rather want to serve ourselves of the observation that if you know as a two-point function, as a function of mu together with all its derivatives which appear here, then you can easily convince yourselves that then all the higher Fn are determined by the infinite system of ingredients, which are the two-point functions plus all its derivatives. So you see, for example, if you take a 6-point function here, you need the derivative of the 4-point function. Then if you take derivative of this equation for the 4-point function, you see that the derivative of the 4-point function needs the second derivative of the 2-point function, and so on. So if you have the derivative, the 2-point function, if you assume the 2-point function to be smooth, and you have all its derivative as an input, then you can solve this equation for the higher endpoint functions in the mean field approximation. And then I have a number now of statements about this. So, namely, if you assume then the 2-point function to be a smooth function in the interval which we are interested in, and there are also some local analyticity in a disk of a certain size, where k is some constant. Typically, one should think of k being some constant larger than 1, and the constant delta, which one rather should think of as being a small constant. And then the derivatives have this typical kind of behavior for locally analytic functions. Then the statement is, if you look at these flow equations, that then we get from the flow equations also smooth functions fn of mu in the same interval, and that these endpoint functions also obey bounds which are of a similar kind than the bounds we had put initially for the 2-point function. So the difference is here that this big constant, which in fact need not be astronomically big. You could do something which is constant between 1 and 10. That these constants then blow up, that there's a bit of geometric blow up here. And there's also a blow up with respect to derivatives, but all these things are relatively mild and well under control. And in fact, the proof is, as I said from previously, you see that there's kind of an inductive scheme going up in n plus L. Then you always know the right-hand side of the flow equation when you want to treat the left-hand side. And if you use this inductive scheme, if you use this as an input and then also this as an inductive input, you can prove these bounds. Now, let's look at an example of these bounds, which is a bit close to what one knows to treat in physics. If you take as a 2-point function, a function delta of mu with a negative sign, delta of mu being positive, which is of this kind here. This is kind of the solution of the lowest order of the running coupling constant equation in quantum field theory. If you only take into account the lowest order contribution to the beta function, then you can verify if you take this delta of mu by deriving it, you get the delta of mu derived with respect to mu is delta proportional to delta squared of mu, because here you have the denominator, it's linear in mu. It's easy to verify this relation here. And let's also look what it means a bit in terms of the physical context. F2 of mu is the bare amplitude. So if bare amplitude for mu equals 0 is something which becomes very small. If you take away the ultraviolet cutoff, it goes logarithmically to 0 because this mu max goes logarithmically to infinity. And the physical amplitude would be the one for which you choose mu equal to mu max, and then you get some delta, which is this constant, let's say, of 1/2, or you might think of something like that. So then you find that this assumption for this choice for F2 mu satisfies the assumptions of the proposition. You get this factorial behavior if you take many derivatives with respect to mu, otherwise everything is quite well bounded. You can look at the 4-point function, which in this case is positive. Because delta of mu is positive. And we also find that we get asymptotic freedom, namely if we take the limit mu max to infinity, as it is explicit here for the 2-point function, as I said, that it goes to 0 logarithmically if we take the cutoff to infinity. The same thing is also true for all the endpoint functions. So if I'm taking away the ultraviolet cutoff, all these functions go logarithmically to 0. So the bare action vanishes logarithmically. The moments of the bare interaction vanish logarithmically in the ultraviolet region. So this is kind of this asymptotic freedom statement. Now you would say, well, where could be already drawbacks or restrictions to the significance of this result? And one point is certainly that you would think maybe this is a theory, the action of the bare action, which is pathological, and in the general case, so not bounded from below or things of similar nature. And so there's a stronger statement which says that you can also get actions which are bounded from below in this context. And this is the following theorem. Namely, basically, if you are much more restrictive on the constants which appear, you can see that you can force this mean field action, this mean field bare action into a form where large field values are tempered by forcing them into a kind of a sign function. So here I have a bare field mean action density, because there was this factor 1 over volume. So in the mean field context, it's better to talk maybe of action densities. Then you can study actions which are of this form, where the powers of the fields then appear in the sign function, multiplied again for the bare action by the inverse field dimensions to get something dimensionless here. And then taking also basically out the field dimension of this A0 here. And then you find that you can take values for these A0 ends, so for these bare endpoint functions which appear in these non-polynomial actions, such that the mean field bare action is bounded from below. It is even globally bounded, because you can take here, it's not no more bounded if you take cut off to infinity, but this is quite a general fact in even the bare action of normal ordinary phi to the 4th theory is not defined without ultraviolet cutoff. But if you put an ultraviolet cutoff, you can see then that this bare interaction here is bounded, is globally bounded. And if you take a factor epsilon here, there's this epsilon also appears here, and this n to the minus 5/4 can be summed. And in order that things work out here, you really have to choose this epsilon very small. Otherwise, you get a bit difficulties with the combinatorics, but there is a finite epsilon sufficiently small such that you can put the bare action into this form. And
sorry, Christoph, there is a question.
Yeah, I saw it. I just
question is from me, Erhard.
Yeah.
Very. Why do you write less or equal infinity in this equation?
Oh, yeah. Thank you very much.
That's just a misprint.
Yeah.
I'm happy. Thanks.
Thank you very much. So it's always, as Pronop Mitter said, it's always good to talk to Erhard. So thank you for this helpful remark. So we are here really very much, far more restricted on the size of the terms which we may allow for and so on. But if we do it, then there is some possibility to get bounded actions, and so at least there is no principal obstruction from this point of view. You get very small but bound and at the same time bounded actions which reproduce this phenomenon of asymptotically free behavior for this mean field of these mean field action moments. Of course, then there's also these bounds on the derivatives of these moments go through as before, also in this context. So we have again this kind of if you take derivatives, these factorials which appear here in a relatively mild form. And since the epsilon has to be chosen very small in any way, so we can even need not talk here about a constant k. And the proof, of course, of this theorem is always the same thing in this flow equation context. We have the possibility to analyze these mean field flow equations inductively. And so we put in this induction hypothesis here on the right-hand side. And the only thing which I should say is that the proof in this case is much more complicated. because it is not easy to obtain this conversions generating power n to the -5 force, whereas the proof of the previous proposition is really easy. For this one, it is not the case.
Christoph, can I ask a question? So
yeah.
I still have to understand what this mean field flow equation is, but so you are now in 4 dimension, right?
Yep.
So what do you get in other dimensions, in easier dimensions? So do you get usual continuum limit in 3 dimension, or do you get triviality in 5 dimension by using this approximation?
Well, in fact, I have not studied the other cases, but in particular, I have not a clear idea what happens in 5 dimensions, more than 4 dimensions. I would think in 3 or 2 dimensions, in principle, you easily get that the flow is contracting, and so nothing. So you get, I think, in 2 and 3 dimensions, they are not. Things become much easier, and you would see that in this simplified context, you can construct non-trivial solutions in the limit where you take away the ultraviolet cutoff of these series in lower dimensions, because these dimensional full factors here, which we have here in the physical dimension of these parameters here, they become contracting. So you get 1 over alphas of higher and higher power if n becomes bigger and bigger, and this makes the thing easier.
Okay.
So I think in low dimensions there's no problem. In fact, to be honest, I have not really thought much about higher dimensions. So for higher dimensions, I would prefer not to make premature statements.
Okay, thank you.
I can note your question. I will think about this. Thank you. So, Erhard, another question.
Sorry, I wanted to postpone my questions to the general discussion. I thought you were there already.
I know. So now 2 other things. There are 2 other short sections. So the first thing is how does this compare to other work on mean field flow equations? And as far as I can see, the thing which comes closest to what I did is the work by Giovanni Felder, who studied mean field action, effective action for this scalar field theory in a resummed form. So he really studied this action, where well, there's again a bit of slight rescaling as compared to my moments here. And he studied this action in dimensions between 2 and 4, strictly bigger than 2 and strictly smaller than 4. And he analyzed global fixed point solutions, so globally defined for all values of phi for this action here. And then there is this fixed point, which is also used to analyze a lot by people who are doing analyzing 3-dimensional Ising model, or whether this fixed point in 4 minus epsilon, non-Gaussian fixed point in 4 minus epsilon dimensions. And his analysis showed if you go with dimension, we go to the limit d equal to 4, then this global fixed point solution tends to 0. And for the model at hand, he could not exclude that there might be other solutions. On the other hand, he also analyzed a closely related mean field flow equation, namely the one for dipole gas. And there he showed that in d equal 4, there even do not exist any other non-trivial global fixed point solutions. So these are results which go in the same directions as the triviality results we discussed in the beginning of the talk. And I think the way out seems that Felder missed certain solutions here. Is not so likely. So I would say it seems likely to me that my method of constructing smooth solutions can be extended also to the mean field dipole gas flow equation, because it looks very similar, even if I have not done this explicitly. And I would also presume that even if Felder could not exclude then other solutions for phi to the 4 in his framework, I would say it does not seem to me very likely that in his framework there would appear other solutions. And so then if I'm looking at what could be sort of ways which reconcile the two things, the first thing is, of course, that Felder analyzed the bare the Wilson effective action globally and not expanded into moments. And if you look now at this bare action, and if it is not in C2 with respect to the mean field value phi, then you cannot really write the flow equation for the resummed object, even if you can write it for the moments. So this would be one way of reconciling the solutions. The second point is that we found solutions, and among those we found these asymptotically free solutions, and these which I showed explicitly in the example. And for these asymptotically free solutions, of course, if you really look now at the global fixed point solution, the bare action in the limit where you have taken away the ultraviolet cutoff is strictly 0, because all moments then go logarithmically to 0. And then this is just having these solutions, but no, let's say, for example, asymptotically safe solutions would also be compatible with Felder's result, because asymptotically free solution, global asymptotically free solutions, which are really fixed point solutions, so which do not depend on the scale anymore, have at the ultraviolet fixed point a vanishing bare interaction. So this may be my comment. So we come soon to into the general discussion. I would just like, as another consistency check, just make a few remarks on the trivial solution. So of course, an important question to settle with respect in comparison with the literature is what happens to the trivial solution in our context. And the trivial solution is characterized by this bare action, so where I do not take into account any higher moments of the field phi, but restrict really to phi to the 4th. I would make a remark which, when you have worked on these things for quite some time with the flow equations, first taking such a bare interaction, which maybe seems quite natural from the point of view of classical renormalizable field theories, becomes a bit unnatural in terms of the renormalization group, because you say there's only one point on the trajectory where all these f2n for all n bigger or equal to 3 pass to 0 for the same value of mu. So this is then at the start, when starting the flow, you would have this very particular point, which only you reach through fine tuning, because it the trajectory finds this form. And now we would like to see in our context then how we can arrange, by disposing of the 2-point function and all these derivatives, how we can arrange for a bare action which takes this simple form where all the higher moments are put to 0 at mu equal to 0. So this would be the task, and then see how the solution to the flow equations behave in this case. And so there is maybe an important lemma first for analyzing this situation. You find if you have smooth solutions of the mean field flow equations for which all these higher moments vanish for n bigger or equal to 3, then you find that in fact for n larger and larger, more and more derivatives of these functions also have to vanish at mu equal to 0. So this is an important remark from the technical point of view for what follows, but because I will not have time to enter into details, maybe just take notice of it. But this remark was helpful, so to say, in finding a good ansatz for this function f2 of mu, which can realize this pure phi to the 4 bare action. And in fact, the ansatz which I then chose was this one, which looks maybe a bit strange, but the strangeness of this ansatz is related, in fact, to some degree to this fine-tuning problem. So here I take the scale parameter mu, which varies between 0 and a very big value. Since the 2-point function at 0 just gets the contribution from n equal 1 here, and then the higher contributions vanish at mu equal 0. And then it is certainly a smooth function mu. It is well defined everywhere. And then if we now define the derivatives, if we analyze the derivatives of this f2 of mu subsequently, in order to realize the boundary conditions of the phi to the 4 bare action, what we find is that these coefficients Bn can then be determined successively for higher and higher n, and we can find that the series that these Bn are determined geometrically, and because this factor which is here is smaller than 1, we find that in fact this series here converges. And as I say, without going into details, these Bn can be successively determined such that we get the simple phi to the 4 bare interaction. There's a certain upper limit for technical reasons on this B1 and B on the 2 and 4 point function, in order that the proof works, which are so we cannot allow infinitely large coupling constants as in the proofs of Fröhlich, Eisenmann, and so on. But still there's a certain margin where the proof works. And then if you look at the behavior of the solutions of the flow equation in this case now, then we find that when we take into account that when we take away the ultraviolet cutoffs, taking the limit alpha 0 going to 0, then the 2 and 4 point function vanish logarithmically in the cutoff, and the 2 endpoint functions vanish as 1 over logarithm of the cutoff squared. And this is then the triviality statement in this context, because it means that the physical endpoint functions all vanish logarithmically when you take away the cutoff. So from this point of view, we are consistent with the literature in our context as far as we can go. And so just let me finish in the last 2 minutes with going beyond the mean field approximation. If you want to go beyond the mean field approximation in this context, you see that in the first moment, the problem is in some sense not, in the first moment, the problem is not really well defined, because if I'm here, I have the flow equation, the mean field approximation. If I go to the original flow equation in this form, you see that here, if I want to define the n plus 2 point function in terms of lower endpoint functions, n and lower point functions, I see that here it is obtained by an integral of this higher endpoint function with a particular momentum configuration. And so the solution to this problem is then certainly not unique, and you need then ingredients to dispose of the freedom which you have. And the ingredients which we have at our disposal are then the various criteria which we should have for the solution. And these various criteria is first O4 symmetry, which is simple to implement. There's no real problem. There's a translation variance, which already causes certain problems. I can all comment on this a bit more. One should have a certain analyticity in momenta, because in the end, one would also go to relativistic space. So there should be certain analyticity properties. There should also growth properties at large momenta coming from unitarity. It is important to construct fully symmetric functions. So all this imposes quite a number of constraints on the construction of the functions. And so probably the strongest constraint comes from choosing the two-point function such that Osterwalder-Schrader positivity can be respected. And the whole thing then should also be put into a context of a bare action bounded from below. So it's really a lot of work which has to be done if one wants to go further. So let me stop here.
Thank you very much. Thank you, Christoph, for this very nice talk. Okay, so I think Erhard wanted to ask a question. So let's start.
Yes. Well, first, if I remember correctly, the Eisenmann-Domnil-Coupin result, it does not work if one tries from the spontaneously broken phase.
Yes.
The continuum. So
yes.
No, I was just thinking of that because your simplest solution had F2 less than 0. So does that in some sense correspond to the broken phase?
Because I can choose it very small normally, and I'm working, let's say, in the massive theory in principle. In the first moment, I would say no. Or I think I can, maybe again, a question which I have not really fully analyzed. I think it might be also possible to go to the broken phase, but I have not really thought about it. There's one thing at least which one should keep in mind with respect to that, that the mass counter term in the ordinary non-broken phi to the 4 theory is also negative. So if you calculate the one loop mass counter term, this is something which also has fallen out.
That's true, even in 2 dimensions, yes.
Yeah. And so I would rather, in the first moment, I would rather see it like this. But I think, well, I would be also a bit, bit cautious to give a definite answer to the question. So I first would rather see it like this, that the mass counter term is of opposite sign. And typically, if you have really small values of these parameters, you can see it also in this scheme that if you took the 2-point function negative, the 4-point function becomes positive. And vice versa, if both of them are small in some sense.
Okay, thank you. Well, thank you for the very clear general exposition also. But I have 2 more little questions, not very deep one. I mean, there has been some industry, I think, talking about the so-called exact renormalization group. The name that comes to my mind is Tim Morris.
Yeah.
I think it's not mathematically rigorous, but do you have any comment on that?
Well, yes, Tim Morris was one of the earliest of the people who started doing this, and also Wetterich, and so this is also quite a long time ago. And well, these people analyze these and they say, well, exact renormalization group. I think the basic justification for this name is that the flow equation itself is not an approximative scheme. So the flow equation, the Polchinski equations, or the Wilson renormalization group equation, these are not. There's no approximation involved in these in writing these equations. And there's this formulation of the equation by Wetterich, which is and Morris also, which formulates things in terms of a flow for unparticularly irreducible functions. And this also does not involve any approximation. There's, by the way, a young guy who recently put also this Wetterich equation on a more firm mathematical basis, because from the by really analyzing very thoroughly the Legendre transform. But I would say that all the work which has been done on these equations over a very long period is not rigorous, and so typically you truncate the system of equations either at high momenta or at a certain value of endpoint function, typically even relatively low, than 4, 6, and then you analyze these equations. And I think there are quite a lot of interesting results which have been obtained over the years from this scheme, but it is from the point of view, from the mathematical point of view, I think it's not really controlled.
Yeah, that was my impression too. So, but I think they try to go beyond mean field by expanding in powers of the momenta.
Yeah, but they never analyze the full system, the full infinite dynamical system, but they rather truncate it at relatively low values of n.
Yeah, so it's not exact in that sense at all.
Yeah. And I think it's really for perturbation theory also. We know that perturbation theory in 4 dimensions does not converge, but we nevertheless know at least there's some small parameter, the fine structure constant or whatever, which is involved, which give you some confidence. But saying I neglect the 8-point function as compared to the 6-point function is probably even harder to get a feeling for than saying I neglect the 3-loop contribution if alpha is very small.
Well, okay. Well, thanks, Christoph.
Thank you, Ed.
So just to maybe follow up on this quickly, so who are the people doing this more mathematically sensible Wetterich equation? So you mentioned
this was a young guy who's called Jobst Siebel, and he just did his thesis a few weeks ago.
Oh, okay, great. No, that sounds interesting. So also like a very quick question about your perspectives. So you mentioned many things that have to be done, but how do you see, like, how doable is it? How do you see the time frame for completing?
Well, this is I'm always very cautious about things which have not been done. So I would say the first 4 points I have relatively clear ideas. Osterwalder-Schrader is much more complicated, and the action is also much more complicated. So maybe the most complicated thing could be Osterwalder-Schrader positivity.
But you think that the tools are there? It's just a matter of somebody.
Yeah. So it's in principle there's kind of a certain functional analysis. Then also, of course, there may be the points that in the end all these things are not sufficient to really restrict sufficiently the theory or whatever. So there may also come out basic obstructions. Let's say I'm moderately optimistic or something like that. At least I would say it's worthwhile trying it.
for sure, yes. No, that looks very interesting. Any more questions?
I would have a question. Hello.
Hi, Giovanni.
Hi. So maybe it's similar to the previous question. So thanks you for your talk. So is there something intermediate between this mean field approximation and studying the full theory, like some systematic expansion in powers of P or something like this, some coupled equation for the first power of momenta or something of this type?
Well, I think in principle, as you say, it's not so far from what Erhard asked, and this is Giovanni. Oh, fine that you participate.
Yes.
So I think that this goes in the theoretical physics context. This goes under the name of effective field theory. So where you do these expansions in higher momenta, but all these approximations they again introduce an element which is very hard to control, in my opinion, because you see, if you go back to this flow equation, you have always there's no no way of getting really around the truth, because here you have this integral, and this integral goes over all momenta. And so you really have to integrate over momentum from 0 to infinity here. And so if I make a small momentum expansion here and then I integrate this somehow tends to give a wrong picture of what happens. Because here I somehow have to know how this thing behaves at very large values of momenta. Otherwise, this integral cannot be done in a reliable way. And if I make, let's say, K here a kind of a Taylor expansion or whatever, then I get again n factorials due to this Taylor expansion, and I can turn things around in various ways. But I think it's hard to get something reliable where you can say then I have something reliable at small momenta, because I somehow in the loops the large momenta will always somehow contribute.
Okay. And I have another question. So is there a way to introduce anomalous dimensions of fields in this mean field approximation or wave function renormalization?
I think this in principle would be possible. And maybe I do not know whether it is unique, but you can do it in various ways. Maybe here I either playing with the dimension of the integral, or the experience, I think, of David Bridges and collaborators was rather that it was easier to introduce in such a context by modifying the power of the propagator than taking 1 over p squared plus m squared, replacing 1 over p squared plus m squared by 1 over p squared plus m squared to the power 1 plus epsilon, things like that. And I think in this way one could try to introduce it and see what you get out.
Thank you.
I think maybe this is an interesting point. Yeah, thank you.
Thank you very much. Any more questions, comments? Yes.
Yeah. So if there is a non-trivial asymptotically free 544, so does it mean
not 544? It's scalar field theory, but not 544.
Oh, okay. In 4 dimensions. But okay. But in this non-trivial case, can I understand that it is constructed around the standard Gaussian fixed point, like usual 543? Because you say it's asymptotically free, so it's
in ultraviolet.
In ultraviolet.
So I would say not. The answer is no.
No.
Because it has nothing to do with this infrared fixed point.
Oh, okay. Okay. And this is a minor remark, but I think Eisenman-Dominale-Copan does not only work for 5.4, but it works for the Ising model. So I think it works for not only not only all scalar field theory, but it covers more than 5 to the 4th.
This procedure here, or what do you? Yeah, as long as you can set up a continuous flow. So what is really important is that you have this continuous flow equation.
Yeah, of course. And I think your model is belongs to the larger.
Yeah, it in principle should, because anything is covered. So as far as of course, what I have also no ideas so much about. So back to Giovanni's and to Erhard's question. If I'm studying bare actions and go beyond the mean field limits, then I could also not only take monomials in phi squared, but also monomials in the derivatives of phi to any power, and then see what kind of a 2-point Osterwalder-Schrader positive, let's say, 2-point function might come out of this. But in the mean field approximation, you do not see this.
There is another question from Erhard.
Yeah, that's right. I mean, maybe that's a little bit crazy, but why do we really need boundedness below? Usually in physics, the hand waving is you start with the Minkowski quantum field theory, and the boundedness below of the potential is somehow related to the positivity of the energy and the possibility to go to the Euclidean theory. Now you are working in the Euclidean. Or do you think it's maybe linked to Osterwalder-Schrader positivity?
Yeah, I think so. I have exactly the same idea as you. Now, you see, if you have come out with something which is a bit non-standard or non-mainstream, typically the reaction of other people is that you may be a bit crazy or whatever, and so yeah, you try to get a bit to look a bit into things which are present in the literature. And if you start from a functional integral definition of the theory, of course you need a boundedness from below. Now, if you could also say from the more physical point of view, I have the system of flow equations. The system of flow equations serves me to find a consistent a system of Euclidean endpoint functions. And if I can continue to Minkowski space, if I'm interested in relativistic field theory, I get a system of Weidmann functions. And if this system of Weidmann functions is okay, I can completely forget then on boundedness from below. So I would also say if we are really there, then boundedness from below would not really be unsurroundable anymore.
I think it's not a physical requirement. If everything else works, if that's possible.
Yeah. So I would also just agree with you.
Okay. Thank you.
Can I ask a question? This is David Bridges.
Oh, David.
Hi, David.
Hi, Christoph.
Hi, David.
Thank you for the talk. I wanted to look once again at your bounds at the end on the mean field equation. I've been a bit confused about what kind of functions these bounds are describing. And I see that, well, I saw already because I looked at this paper for some time earlier. I see that you have these ways, for example, of rewriting a smaller class of functions in terms of the sine of phi squared and other things. Can I just look at that again and just ask a couple of questions?
Somewhere
so
here.
Just beyond this, you've got your bounds. Back up a little bit. I wanted to ask, the initial bounds that you have, 1 and 2 in this proposition, they describe a function that where the series for the power series would describe a function of phi which is analytic in a disk. Is that right?
Yes, because these. Well, here you have. I need these here, and then you see. So I'm in this case, I would look just as the functions without derivatives. So
I see my confusion. This d sub mu is not a derivative with respect to the field.
No, it's derivative with scale parameter.
Okay, good. That's what I.
But the answer to your question is nevertheless yes, also because then the Fn is just geometrically bounded. And then we see if phi is smaller than 1 over k, I get convergence in phi.
Yes, I see. So it is bounded. As a function of the field, it is it is a analytic in a disk.
Yeah.
Good. Okay. Now, so of course, if you're thinking in terms of functional integrals, and I'm kind of stuck on that line of thought, then you want it to be defined for all values of the field, and the expansion in the signs achieves that, right? Which is very nice. Can we just look at that formula? So this is a smaller class. It's a smaller class within the one you've just described.
Yeah.
These guys do converge for all values of phi.
Yeah.
Good. But if I differentiate with respect to phi, then I get extra powers of n. And I guess that's still okay, right? Because you've still got this geometric factor.
Yeah, but here, if you have in the sign, I have the power phi to the n.
Oh, right, phi to the n. Yeah, that's not so good. So
not so good, yeah.
Right. So so that's why these functions are C2 in phi at best. Is that right? Is that what you said?
For example, if I said the relation with the results of Giovanni Felder, I said, for example, this would be could be an obstruction here for this thing, because I would say this is not C2 in phi. Yeah? This object.
Yes. Right, because that rather invalidates the flow equation that you you were trying to use to derive this.
Yeah. So
is it? I mean, are you hoping that this is a kind of a generalized solution to the flow equation?
Yeah, I would think so. I would also think so that if you you can try to derive a flow equation where first also in your functional integral you make die out large field contributions artificially, and then you first derive the flow equations in this case, and then you take away this regulator. So some procedure of this kind, where again you say you first start from a regulated version of the functional integral where you take out large field contributions, where the large fields are nevertheless they are multiplied here by inverse powers of the cutoff. So you cut off this a bit sharper, and then you derive the flow equation, and then take this cutoff away. Then you get again the flow equations from an additionally regularized starting functional integral. So I think one could do things of this kind. Now then we get back a bit to the question also of Erhard. What would you really have to have from the point of view of the models we are after? Because I could also say, well, for me it's much more important to have the flow equations for the endpoint functions, which allow to reconstruct the Weidmann theory, and I'm not really completely linked to the bare action, but well.
Okay. And then you also looked at the expansion expressed in terms of inverse powers of 1 plus phi squared, or something like that. This was your ansatz for G for this for the second moment. What can I look at that again?
Where was this? Inverse powers of phi squared?
You wanted an ansatz for the initial the Green's function, basically, the initial 2-point function. And you wrote it as sum over powers of 1 over 1 of...
yeah, this one.
Yeah. This one, right. And that's, okay, that's in mu. I see.
Yeah, that's in mu. That's in mu.
I'm always got confused between mu and phi. Okay, so I see. So that's that worries me less then. Okay, I've got it. Thank you very much. Thank you. It's very interesting. I'm wondering if all of these clever ways of rewriting have anything to do with, I guess, using things like Pardé approximants and so on in order to get outside the to get better convergence. But anyway, I think that's very interesting. Thank you.
Thank you very much, David, and thank you also for looking at the paper. I think you were the first person to have looked at this paper a bit more thoroughly.
Yeah, but you can see that I still have my points of confusion over it. That's good. Thank you.
But just if I really may just that I can come back to this formula here, it's really from the point of view of the renormalization group, at least if you look at these regular, locally analytic solutions, it's at least it's interesting at least to see that you are led towards relatively sophisticated, or maybe at the first sight even slightly unnatural ansatz for the 2-point function here, because this is in fact a somewhat strange thing for the 2-point function. And I saw that I really need something of this kind in order also to satisfy these conditions here, to find this so-called trivial solution, which in fact you would first think is the easiest one to find, because just putting phi 6, phi 8 and so on equal to 0 from the point of view of classical renormalized perturbation theory, this would be the easiest things to do. But from this point of view here, it's something relatively complicated.
Mm-hmm. Mm-hmm.
Okay, are there any more questions, comments?
Yes, may I have a
Wojciech, hi.
Yeah, so if I remember correctly, Polchinski approach was perturbative. So I'm a bit confused. Which part of your discussion is perturbative, which is non-perturbative? Is it like this, but in this mean field limit, things get non-perturbative? Or
No,
did I get it wrong?
here it is, I did not say anything on perturbation theory here, apart from this remark. Let me say, where's this remark? So as you say, Polchinski, I think these equations in some sense are already implicit in the work of Wilson around 1970. And they are first explicit, the implicit structure of the equation first appears in a paper by Wegner and Houghton in, I think, in 1972. But where it was applied to Ising type models. And Polchinski 12 years later wrote it again, and he really saw the merit of this paper was that he really made a bridge between this non-perturbative renormalization group framework and perturbative renormalizability. And then he said, if he now uses in perturbation theory, and this means then this is expand also in the number of loops, which are mentioned shortly, then you can make statements about renormalized perturbation theory. But I did not talk about this today here, because we had the mean field approximation, but then we made non-perturbative statements.
I see, but in your conjecture, I understand the conjecture is that you can have a scalar field with some perhaps complicated Lagrangian, unusual, not phi to the 4, which is asymptotically free. Should it be a perturbative, a non-perturbative statement, or should one first try to solve it perturbatively?
This statement would then be exposed in a non-perturbative context.
I see.
Of course, you can always then say, if it is asymptotically free in the ultraviolet, our experience shows that perturbative calculations then are good, at least in the ultraviolet, for sufficiently high energies. But the statement itself is a non-perturbative statement. But of course, here it's only mean field, and then it's a conjecture, or what you said, about a non-perturbative.
Okay, then maybe a little bit different question. If I take something simple, so to say, like phi to the 4 in 2 or 3 dimensions, will I succeed in constructing it non-perturbatively using this approach of the flow equations? I don't remember.
I think there's some hope that this might be possible, but this has not been done here, because again, all these problems which I had in the end of the lecture always, I think so, the mean field construction, this was already Hal's question, in the mean field approximations, these non-perturbative statements become simpler in 2 and 3 dimensions, but then all this is also present in 2 or 3 dimensions. There are still symmetry properties. And I also need this positivity statement. So all this should also has to be settled in 2 or 3 dimensions.
Okay, thank you.
Thank you for the question.
Thank you very much. Yeah.
Can I ask a question?
For sure.
Thanks, Christoph. That was a great talk. One question, a naive one, is can one think of this mean field approximation as a hierarchical approximation? Is it exactly
related? In fact, yeah, it's related. And there's other work about these hierarchical models by for example, Christoph Kopper and Antti Kupiainen and so on. In fact, sometimes people say then it is the same, but I think there are a lot of hierarchical approximations, and these hierarchical approximations also consist in neglecting fluctuations, and depends a bit on your particular setup, which kind of fluctuations you neglect, because normally if you think of this in terms of block spin transformations, then these hierarchical approximations consist in neglecting fluctuations which go across the boundaries of the blocks in which you organize the functional integral. And this is of course related because it's also neglecting fluctuations, but these are not exactly the same fluctuations. Whereas this, what Giovanni calls the local potential approximations, this was really exactly the same thing which I did here.
Thank you. Thank you very much.
Thank you.
Thank you. Any more questions, comments?
I have a question.
Yes.
The mean field has, I mean, the expression mean field has many meanings. And so here you're using a very specific one. Or
well, but I would say it's maybe well, if you admit that there is a standard one, I would say it's close to the standard one. That is to say, you really take the endpoint function, the mean value of the endpoint function over the volume, and then you divide by the volume, and then you take. So this would be, for example, the mean field magnetization of a ferromagnet. The definition which you have in mind intuitively corresponds to what I'm.
I think in other communities there are other meanings. So I mean, for instance, one meaning is that everybody interacts with everybody with the same strengths. So I guess this
would not be the.
This is a different.
Yeah, this would be a different one. Yeah.
Yeah. So what does one learn about the true model from the mean field from your mean field approximation?
Well, this is always, of course, then the question for any approximation. So normally, well, people. It depends on whether you think. Normally, you would think if you are not close to second order phase transition, the qualitative properties of models are well described by this mean field approximation, and I think this is also something which is confirmed in physics. So physicists typically accept that the mean field approximation, in this sense that you neglect fluctuations of endpoint functions, gives good answers to physical questions if you are not close to a second order phase transition.
Thank you.
Thank you.
Okay, more questions? Okay, I think we exhausted the questions and the speaker. Thank you again, Christoph. This was a very beautiful talk, and yeah, so let's thank Christoph again and close the seminar.
Goodbye, thank you.